Some of these are funny.
I have a headache just reading that.
We know what microwaves are, and we know what, hold on. There's infrared light, and there's violet light and red light, because it's the galaxy. UV, HIV, sulfur, okay, hydrogen, X-ray, huh? We don't know what's in the other galaxies, but we know, we can hypothesize based on clustering of atoms, of like how elements form. Alternate parallel universes, yes. Yes.
You believe in evidence?
Protons, up quarks, down quarks. This is like trippy. High energy radius, I don't know what that was. Oh my gosh, so fast. Neutrino. See guys, I could have made you memorize to yoctometers, but I made you go to picometers, and that was it. 10 to the negative 24, that would be 24 places from base.
Where?
And you think I hate you, but I don't. We got to 9. On the other side. I'm going small.
No, like, what? Yeah, I want to like, where in the world can you find a 7 meter?
Man, I am not Google. These are questions you can ask Google.
Giant earthworm, 7 meters. Are there really giant earthworms that big? Where?
What's it called? The Alaskan bullworm.
All right, and get your last look at the galaxies.
I need a little bit more time to digest.
Okay.
Yes.
And then we're going to come back to chemistry, chemistry world.
What's in quail? It seems like they're missing a lot of stuff down in India.
They were 16-year-old twins who programmed us, so give them their kudos.
Whoa, 16-year-old twins.
Yeah, they're your age, and they did this. Basically, I'm telling you to get on their level. I think they did a project.
They got paid.
Oh, somebody probably like bought them out afterwards and said, let's
I was
come
going to say, they need like 120 for this project.
$120.
Okay. All right, my little yoctometers. Halfway close your computer so I know that you're with me. And let's chat about some of the periodic trends that you discovered. Why do you think I made you look at this first before I started yelling?
So we can have something to contribute to the book.
Okay, so that you can verbally contribute some of your observations. What else? What'd you say, Ethan?
So we can get on understanding.
Okay, so I'm not introducing everything new, and you're like, oh my gosh, where do I place this in my little categorization of my mind? You're actually thinking about how to connect these dots. What else? Yeah.
It's our second time reading.
Yeah, or, second, you guys did a little bit of part 3 about the interactive you guys did together. You've now seen this on the atomic model, which, I mean, I don't really have a lab for this, let's be honest. They're this teeny tiny, I wouldn't be able to show you a valence electron, right? So I wanted to at least give you a bit of a representation of it. So, these are your 4 periodic trends. How do they roll? Okay, sorry, in a square. So what's your right hand? Atomic radius. And so this is the stuff you wrote down on Friday. If you were not here Friday, I'm rapidly going through this beginning part, and then we're going to start applying it, and then we're going to finish up problem set 6. So, atomic radius increases to the left and down a group. As a comparison, you guys can put your hands down now, thank you. Okay, so as a comparison, you guys just manipulated some variables of, I think, I saw some people doing like potassium and krypton, right? So when you look at potassium and krypton on that little simulation, which I just put right here, okay, what do you notice? Who's bigger? Okay, potassium is bigger. How many, how many electron energy levels do they have? How many electron energy levels? 4. They both have 4. So you think 4 clouds of electrons, they probably should be the same size. But they're not. Why? Thank you, Chris.
The effective nuclear charge.
Effective nuclear charge. We can rephrase that and say, how effective is the nucleus's charge, right? How effective is 19 protons at sucking and pulling in the electrons around this versus 36 protons that are able to attract out here. Who's more effective? Krypton's nucleus 36 is much more effective at pulling in 4 energy levels worth of electrons than these poor 19 protons are. So the premise behind all this is that protons attract electrons because opposites attract. That's the basic premise. So you have 36 positive charges. You can attract your valence shell, which is the outside shell, better than you can if you had 19 protons. That term is called the effective nuclear charge. Okay, do note that, star that. You guys write that down Friday. Question so far?
Why do they have the same number?
A valence electron, or the shells?
Yeah.
Because look at the periodic table. Look at the periodic table. Potassium's there, right? So that's first, second, third, fourth. So it's like 4s1, right? Boom, 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 boom. Krypton, 4s2, 3d10, 4p6. Doesn't matter they have more electrons, it's not that they have the same orbitals. Well, they basically are arranged from the inside out the same exact way, it's just that tail end that's a little different. So you can see that, and you see I've compared across the period, right? You guys write down nuclear effective charge Friday, and what did you write next to that? I said it was a factor for a period or for a group. You should write this down if you didn't on Friday. I said nuclear effective charge.
Period.
I wrote down this information, or I told you guys to write this down. I said I would elaborate Monday. It says nuclear effective charge is a period factor. And it's basically saying how effective is the nucleus's positive charge at, effective is it at pulling in or attracting the valence shell of electrons. If you have more protons per energy level, it's going to be a stronger pull. What happens to the radius? Decreases the radius. All right, same story, different trend. What was the second trend I had you guys look at here on your simulation? Ionization energy. Okay, what the heck does that even mean? I had somebody look it up. I think somebody else did. What does it sound like it means?
Ionization energy?
Yeah, what does that
The
mean?
amount of energy it takes to attract electrons from one atom to another.
Okay, it's very, very close. So it's the amount of energy it takes to remove an electron. All right, so if Brandon back there had 7 cookies and he loved cookies, would he willingly, probably, with that love of cookies, would he willingly give us a cookie? No. He's not that nice. He loves cookies. And it's just something genetic, okay? So Max up here had 1 cookie and he's like, meh, cookies, I prefer brownies, right? Would Max want to give up that cookie?
No.
He'd be fine with it. Okay, work with my analogy here, work with my analogy. So what I'm saying is if I have, remember octets are kind of golden rule. If I have 7 electrons, ain't nobody gonna take that electron from me because I'm so close to octet. 8. But if I have 1, I mean, I could care less. So Zach, stop, thank you. So I could care less about my single electron and I might be able to give it up easier. Well, how does that play into this term ionization energy? So if I really, really, really like my electrons, do you think it's going to be associated with a high energy or a low energy?
High.
High. Do you think if I have a large atom, think about the atom, think about how the atomic radius trends, do you think it's easier to take, let me actually go back to that example. Do you think it's easier to take this electron from potassium, remember the attractions with the nucleus, or this electron from krypton?
Krypton.
Easier to take it from potassium, why?
There's only one. And then
It does relate to the number, but it also relates to the attraction of the want from the nucleus. This electron is much farther away from the nucleus, right? This electron's a lot closer. Which one do you think is more attracted to its nucleus? The closer one. If you are closer to your nucleus is really, really well attracting you there. It's going to take a lot of energy to overcome that attraction. Comparatively, potassium's pretty far out, so not like far out, like cool, but like away, okay? So you have your single electron here. It's pretty, a large distance away from the nucleus, not as highly attracted. So you can see the differences here as well. First ionization energy, 400 kilojoules per mole. burst ionization energy, almost 1400. Much more energy. But why?
There's more protons.
Okay, because there's more protons and it's closer to the nucleus. It's smaller. So there's reasons, yeah. So there's a lot of reasons behind it. But you have to be able to verbalize it. If I say, why does a trend work the way it does? And you just go, that's not going to tell me anything. I need you to explain it. Yeah.
So smaller is better for atoms.
Smaller, I won't say there's a good or bad. That's like personifying it too much. Smaller generally means that it comes with a lot of other characteristics like high ionization energy, high electron affinity, high electronegativity, all the ones that go like this. Okay, so keep going with this example for a moment. You guys just told me, basically, I'm still considering the period trend. So the period trend, again, is going from potassium over here. I'm looking on the periodic table now. Elijah, with me? Okay, potassium to krypton. What do I still have? How many energy levels? 4 energy levels. So it's not about the energy levels that changed. It's about the
Number of
orbitals are still the same. It's still like 4 energy levels. Protons, it's just simply the effective nuclear charge that's really controlling the things that are the trends that are occurring across the period. All right, so let's continue, but let's do potassium and you guys tell me what's below potassium you guys want to mess with. Say again? It's acid below potassium. Rubidium. Okay. Let me go a little bit more extreme. Let me do lithium and rubidium. Okay. Oh, I have to unclick that. I got it. Okay. So, you see my example. You see a size difference. Why is rubidium larger? Raise your hand on this one. I need some structure here. Kindle. Okay, change mine. Yes.
As it goes down, it increases.
So you are saying the trend as a fact. That is a fact. As you go down the group, the trend increases. That's not the explanation. We're learning how to explain it. Go for it. Thank you. That's it. As you see, 1, 2 energy levels on lithium, right? Look at the periodic table. My question, I forgot. So we're going to go with that. So I can't remember how I phrased it, but let's work with this. So look at the periodic table. How many energy levels are in lithium? 2. So that's 1s2, 2s, 1. 2 energy levels. That's it. But then you look over here at rubidium. Ain't nobody got time to go all the way down there. Let's just do krypton bracket, right? Yeah. And then what is that? 5s1. How many energy levels do I have? 5. Okay. So it's only bigger because there's just more electrons to accommodate, and they follow Aufbau's rule and they go in order from first energy level to 5th energy level. So that's the one reason it's bigger. Okay? Yes.
So when you look at that, when you say 5, it has 5 valence electrons, but it has 5
energy levels.
Okay.
And I'm counting those. These are drawn in like our elementary orbits, like you would have drawn in middle school. We know now that they have those funky shapes that you have to think about. All right, so regardless, this is going down a group. You get bigger because you have more energy levels. Second note, look at the, I'm sure it's probably hard to see, but I'll tell you. First ionization energy for lithium is 500-ish. Okay, over here, 400-ish. So why is this electron easier to get than this one? Whoa, give me a hand raise, Josh.
Because it's farther away from the nucleus than lithium.
Okay, so it's farther away from the nucleus.
The effective charge isn't as great.
Whoa. Okay, we're talking down a group. Can we say effective nuclear charge when we're going down a group?
No.
Okay, that's what I want you to see. As I change it up on you, I'm now going down a group. You guys write this down. Effective nuclear charge is how you explain things across a period, because you got to keep a constant, right? The constant is the energy level, and you're just changing protons as you travel and, go from potassium to krypton as we did earlier. Now we're going down a group, and I told you guys to write this down. This was a group factor. I know, Josh, I know you got it in papers. I just saw this. So this is called the shielding effect. So, Austin, come here, man. All right, I need you to be, I gotta find that other magnet. Where'd you go? Well, Santa, you guys come down. Okay, so, I need you to be my nucleus and I am the valence electron, okay? Me, I'm the valence electron, he's the nucleus. And now these are magnets, so I'm trying to resemble. Okay, opposites attract. Okay, these are really strong neodymium magnets. Okay, so they definitely will stay. Alright, so if we have one energy level, here's with me. Okay, we have one energy level here. Nucleus, you ready? Attracts to the valence electron. Okay, I need this for an example. So, one valence electron, strong attraction between the protons in the nucleus and the valence electrons. How much energy do you think it's going to take to rip this electron off the shell? A lot. There's a lot of energy here. But then, I have multiple energy levels, okay, between us. This is called electron shielding. There's 5 energy levels between us. So, I can't find you. Oh, I don't even know my nucleus exists. I'm in every atom. Okay, so that's the thing. It doesn't take much energy to whip off that one because there's no attraction. I can't even find my nucleus.
Have you ever gotten it?
No.
Because the thickness is that
So-
change.
All right, so that's called. You can get on my Amazon for $10. I got like 8 of them. Yeah. No, for like 8 of them. Okay. Back with me. I'm trying to do some oral interactions so you can see what I'm talking about from a perspective of a textbook. So what did I call the textbook? 5 energy levels, and that causes the shielding effect. Okay, so on that example, I think, Josh, you were picking up and I interrupted you. You're going to explain that now. Why does this one require 400 kilojoules to remove, but this one requires 500?
Because there's more energy levels in between that valence electron nucleus than the others.
So there's a lot of shielding effect occurring in this atom. There's only one energy level here, not much shielding effect, so the protons can exert its full attraction on this electron, whereas the protons don't even know that outside electron exists. It's so far away. Yeah. This is actually, this is like the paper, and this is like the textbook. Perfect. Yes. Who's feeling okay? Give me a thumbs up. Okay, the conversation piece that you guys have and then me connecting the dots, I'm hoping is the key here. All right, because I know you guys are like, 4th period chemistry, what are we doing? Okay, so work with me here. In terms of one more example. Oh, this is the last thing you guys did. Let me see if my computer's gonna work with me. So, oops, not that one yet. So in terms of the ions formed, you guys manipulated some data. I have this in my hand. All right, we're just gonna leave that there for a hot second. Okay, so you guys draw this for yourself. Draw lithium as it kind of depicted it on the screen on the simulation. Draw lithium as it depicted it on the simulation. How many protons does it have? 3 pluses. And what does it have around it? 1, 2. That's like 1s2. Okay, what else? 1 more. So that's 2s1. Okay. How many valence electrons does lithium have? 1. How do you know that? 1 on the outer shell. I'm not drawing you pictures all the time though, right?
No.
Likely what?
Yeah.
You will probably be seeing it like this because you can imagine how that relates. How can you tell there's 1 here? There's only 1 in the n equals 2, aka the valence shell, the very last energy level. So there's only 1 valence electron here. Alright, so the 4 is the breaking point. If I have less than 4 valence electrons, I tend to lose them. If I have more than 4 valence electrons, I tend to gain until what? Octet, until 8 electrons. So what's lithium going to likely do? It's going to have to lose. There's no way it's going to gain 7. Nobody's going to give it that much energy. So as it loses 1 electron, lithium still has its 3 protons because nobody touched that. And it still has its first energy level. But what happened to the outside one? Right. So the cloud is just there because electrons live there. Once the electrons are gone, the cloud no longer exists. Yes.
So when you have it written down, you just look at the, I don't know, it's the exponent?
Yep, the exponent is the valence electron in the second energy level. in the s orbital. One electron in the second energy level in the s orbital.
And then when you see, like, when you group it, you would just look at the last.
If you group it as in like 2s2, 2p
Yeah,
something,
and you see which one is the last valence electron.
I will show you that example down here. Give me a second, okay? Question?
What?
You have videos to watch. Okay, thanks. All right, so what do you guys see happen to the atom size? It decreased. Okay, so cations are smaller than their parents. I'm going to say parent because we kind of say the parent is what it originally exists as, and then as the ion forms, it changes size. All right, and that's because, one, it loses the cloud, and it has a significant pull from the 3 protons that still exist there. Same story, flipping the script though. So let's do fluorine because it's small. Fluorine. How would I draw fluorine in the same manner? Fluorine, upper right hand corner. Draw this out for yourself. Hold on. F has how many protons? Let's start with there. You guys got like 18 periodic tables in front of you. 9 protons. Okay. You have a bunch of periodic tables right in front of you. So, fluorine is 1s, 2. I'm just drawing the electrons like orbits. 2s, 2. And then this is just the second energy level, so I'm going to keep adding my p there as well. 2s2, 2p5. 1, 2, 3, 4, 5. Okay, I just kind of spaced them out. So that was 1s2, 2s2, 2p5. But because the s and the p right here are still in the second energy level, they're still just of approximately the same distance from the nucleus. Alrighty, so fluorine, how many valence electrons does it have? 7. You guys, I'm really feeling like if you keep listening, you're going to do grounds for your response, because I have questions just like this. So, 2 plus 5 is 7 valence electrons. Is it going to likely gain electrons or lose electrons? Gain. 1, right? Just 1? Okay, so if I add an electron right here, I've added an electron. What charges do all of these electrons have? Negative charges. What do negatives and negatives do? Say again? Repel. Okay, thank you. As I think Austin knew I needed that, and he was like trying to. Okay. I can't touch it. It's repelling. Okay. So this is what's going to happen, and because they can't get close together, they repel. So what happens to the size of the atom? It's going to just go up a little bit bigger, so it's going to get larger. Don't you mess up my neodymium. Thank you. Okay, so at that point, the atom is stable because it has octet. Well, it just rolled down. It's still there. Okay, you can say that same analogy with every single cation and every single anion. What is likely on the periodic table? Which groups are likely to form cations? Which groups?
The halogens.
Cations have positive charges. Paul, thank you. Alkali, alkaline earth. Okay, transition metals for sure, actually, absolutely for sure. But they're weird, so we try to skip them for the moment. Who has, okay, oh, maybe you guys didn't catch that. On your warm-up, listen up on this one, be quiet. You had this knowledge you gained last week, or maybe the week before. The valence electrons equal the group number, because that's where you stop, right? 1s1, 1s2, 2s2, 2p1, so that it builds on itself. So, how many valence electrons does carbon's group have? 14. Ignore the D block. How many valence electrons? What group is that? 4. It goes in order. 1, 2, 3, 4, 5, 6, 7, 8. How many valence electrons does this have? 8. How many valence electrons does boron's group have? 3. How many valence electrons does fluorine group? 7. How many valence electrons does beryllium? 2. Do you see how predictable it is? That is called the periodic nature of the periodic table. You know, like periodically I'll go to the gym and run 5 miles. once a week. That's going to be the trend. It's every week. I do it one time. That's why it's so periodic, as you can see on the periodic table. Okay?
So what are the transition metals?
The transition metals, they fit in the inner d orbitals. So like that's where we go from 4s2 to 3d10. They act a little differently because they stash their electrons in different places. All right, so pull out your PS6. Let's chat with that real fast. You guys are going to tell me which ones you have questions on. You're going to finish that up. And then, one second. Then you guys will get into your groups to finish discussing your 5-minute conversations you're having with the class tomorrow. Okay? I have 30 minutes with you, and I need like 2 right now, okay? Questions?
Okay, so on the table where it says most metallic, how do you find that?
So that's, I knew was going to be the question of the day. Metallic, if I tell you, metallic means, okay, here we go. Metallic means likely to lose electrons. Stop being rude. All right, so if I tell you metallic means likely to lose electrons, which side of the periodic table is most likely to give up electrons? I want to see a left and right. Go like this for me. So if I'm willing to give up electrons, that means I want to lose them. Some of us are saying this way. What do all of these want to do? To become octet, right? So what are all these going to do? Likely lose, because they have 1, 2, or 3 valence electrons.
So once you hit 4,
That's you're on the fence. 4, we try not to deal with that because that's too big. So metallic nature is going to increase this way because these are really likely to lose electrons. These are like, heck no, I'm on this octet, right? And then what size atom is really likely to lose its valence shell? Large or small?
Small.
You guys are just saying things without even thinking.
Large.
Why large?
Because
this
it's
is
further
a
away.
nuclear fault.
What's that called again?
Shielding.
Okay, so the largest atoms have a lot of shielding. They don't even know this electron's even out here. They're like, fine, go party, go do what you gotta do. All right, so as you can see, it follows the same trend as
Oh yeah.
atomic radius. Okay, so basically, metallic nature is following the same trend as atomic radius. So you'll see that on your chart. All right, continue. Work on your own. PS6. Let's go. I'll come around for individual questions.
I just have a question about whatever. Can you first see what it was like? Which ones are most in which form of transition being circular? That's what's in all of our ones.
Cobalt, titanium, uranium.
Is that why they're? Is that why they have like uses for them? Like that's why copper is. Copper's fluid.
Different targets. My goal is for you to knock out concept 6 in class. Goals, right? It's due tomorrow, but why not? Why not right now? I want you to get started so you have a nice day.
Oh, I have another.
I'll be right there. Okay, on your website, the actual
There's also good tools that are down for the after. Oh, so we're gonna. It's just showing you. They're right there. I did. But I thought it was all the same thing.
So the largest is the same, the lowest version is so when it goes down. And then the first two are.
I'm trying to memorize. Yeah, I don't.
So they're the same source.
I know we get a document that has stuff. But it's all up the furthest. Literally,
I know you're part of That's why video is that's your priority.
Well, we finished the problem set now.
No, you can't finish one session.
Well, I know some of this stuff.
You can finish up some that you feel comfortable with, but you're a little bit on board with camera, so I want you to make sure you're learning from the old stuff as well. Okay?
No, it says why does it have lower the VA is there.
Which one? One marker?
Oh, I thought you were going to take
Outline of the So, this should be the last time I'll probably yell at you. Sorry. Listen up for me. Eyes on the board in 5, 4, 3, 2, 1. Thank you. Last thing I'll say for now, because the rest of the time for you guys to work. I linked this under Friday, February 17th. Here's your link for the group work, periodic trends and properties. It was a Bitly address, and the Bitly stopped working because the school's the school. And so whenever you click that, that will bring back up that part 1 through 4 assignment. Just focus on making sure that tomorrow you're confident and calm and able to explain whatever you are explaining on your part 4 question that you selected. I do have a couple people that need to be adopted into a group. So if you are not in a group, raise your hand. Zach, Max, Rachita, you're with them now, right? Okay. So I'll get you guys adopted in a second, okay? Back to you. Finish up as much as you can on PS6. I'm taking it tomorrow.
Peace. Peace.
You're not here Thursday. Come down.
Yeah, you already know.
Okay.
I wasn't going to say that.
Number 3 is the periodic mystery.
So Max,
It's me, Nayeli, Austin, and Connor.
can you adopt Max?
We don't watch it. With Simon's paper, they were saying that like we are legally adopted. It's a consent form just in case Austin tries to talk about how he used to be used. Because he was yeah, Austin is but yeah. Austin. We're adopting Max. He has been wanting to
Also, do you have duct tape? Because I'm gonna have to duct tape this. I do not have the duct tape. I think I have masking tape.
Basically, our question is talking about if people change
I don't know what the match is.
change one element into another, like which each other, like basically as a possibility.
So I just had it this morning, and that's when I noticed the thing was ripped. I probably should have moved it. Today's the 19th. Sounds good. Thank you.
That's also because we talked about both sides. We talked about both sides.
No, talk about like the ethical violations.
We're talking about ethical violations, environment violations,
Economic stress, environment destruction.
so like turning like oxygen into gold. We were saying that like companies could like Jared would lower their prices because they have a surplus of gold to make sure they're happy with the market that because they can't use it to sell. So people would want to turn oxygen into like water or oxygen into like an element that we can use
And
as food.
people that have previously bought gold things,
Yeah.
the cost of it goes down because trying to resell it for
Higher value.
Zachary, my son, come here.
What do we just look at you? You good?
Oh, I'm sorry.
Chris. Oh, it's
Actually,
part
no.
4.
My son. How old are you? How old are you?
You put 3.
December what?
It's
all there. Oh my god. It don't matter.
Yes.
So you have the answers to the questions we did on Thursday. So that's part 2. Yeah, well, we already took them. Okay, and then Austin's gonna, yeah, and then Austin's gonna do the periodic table.
Thank you.
And then we appreciate it. And then we individually have the little principle thing at the start.
Yeah.
And then the only last thing we have to do is like just research our individual topics. And you know what we should do? We should put all that info, put that info in the group doc. And then we need to share it to you.
The ethical violation.
You need to
that's the
group
one
chat.
that-
Make sure we get this.
Yeah.
I'm gonna share it to Max with that. You need a group chat.
We feel all sure.
Does everyone have an iPhone? Because I'm not sure.
Max, if you don't have an iPhone, I know, but sometimes people get like. So funny. No, that'll to this day that was probably one of the funniest things I've ever heard Austin say.
Max, you want to read the something?
I love you.
Oh, Zach. Alright, Brian. I'm giving you guys some thoughts.
Like should it be used for technology, hardware, for stuff like for purposes besides the labor?
Yeah, I just got to get that. I haven't got a case of it, so I'm really like, I don't want to scratch it or like fix it.
I can't even hold like sticks and see
You're not allowed to.
Alright, so you guys are continuing to collaborate on part 4. Collaborate on part 4. You know what, can you just put your ice in and think about it here and just a towel? I put it in. Oh, wonderful. Then hang up the towel.
So, I forgot, we're gonna...
Listen,
When I was doing PS6, I worked ahead and did the rest of it by accident.
That's unit review. Hold on to that because I'm going to be taking this on test day.
Okay, so I can also, yeah.
So you don't really need me to review, except for nuclear.
The only thing I didn't understand was the A to C.
It's that notation type that gives you information about mass and atomic number. So like sodium is atomic number 11. It has a mass of 23 generally. That's called the A to Z notation. That's the A number, that's the Z number.
Oh,
Do you remember that?
yeah.
It's called the A to Z notation.
You guys had 2 different answers. What is it, what? I don't know. Awesome.
Alright guys, this kind of tells me that you don't know how to use free time. Some of you guys are, some of you guys are not. So either do finish up PS6 or work through part 4 of your collaboration. Those right now are your 2 options. Please do not abuse the time or you start to tell me you never want free time in your life again. I try to treat you like adults, but, you know, work with me here.